Yeah, I think if it said it starts precisely at.
The recording.
Well, I think Anne-Marie said that the broadcasting and recording starts at 1:40 sharp, so somebody needs to know exactly when 1:40 sharp is, as your watch is precise.
Yeah.
Of course, yes. And so maybe it might be better. I don't know if one side. I don't need to actually operate the computer, I don't think. So I'll just be. That's it. Thank you very much. Yes. Well, this is the kind of work one does. Right, yeah. Yeah, that's right. Oh, we'll talk after.
Yep.
Yeah.
Hey everybody, thanks for coming. I'm Julie Whitcover. I'm a scientist here at ITS, and I have the great pleasure of introducing John Sicko to give us a talk on biofuels carbon balance. Land use change, I just have this feeling that land is going to pop up in a discussion somewhere, and I know it's near and dear to many people's hearts here and elsewhere. John got his doctorate in mechanical engineering from Princeton University, and then has had quite a career in a number of different institutions, being transportation director at the American Council for Energy and Economy, and senior fellow for automotive strategy at the Environmental Defense Fund. And he's currently holding a joint appointment as research professor at the University of Michigan and professor of practice at the School of Natural Resources.
Thanks a lot, Julie, and thanks to ITS and other folks for hosting me out there, hosting me out here today, and thanks to all of you for also showing up and your interest, and I'll definitely look forward to questions and conversation as we go forward. My presentation is largely based on a paper that came out in the journal Climatic Change a few months ago. The citation will show up on one of the slides. And it, the title is Biofuels Carbon Balance, main title. And it represents a very fundamentals-based, really first principles analysis of biofuels as a carbon mitigation strategy. There's been tons of work on biofuels over the years, and towards the latter part of the talk, I'm going to talk about some of the history of how we got to where we are today in terms of the kinds of methods that have been used to try to say, okay, what went wrong? Because you'll see, the gist of my talk is that the methods that we've been using based on life cycle analysis have misled us in many ways. So let me talk about what I'm going to do today, and specifically I'll spend a little bit of time talking about why I went down this road leading to this analysis. Before I do the formal analysis, which is simple but perhaps sometimes conceptually challenging to digest, I'm going to just do a little thought experiment that gives the gist of the analysis. Then I'll walk through formal analysis as laid out in my paper. Essentially, it deconstructs life cycle assessment as applied to biofuels. I present a very simple box model, first-order model, of the coupled bio and fossil fuel systems as they interact with the atmosphere. And the goal was to identify conditions under which biofuels might have a mitigation benefit. And the upshot is the need for essentially an increase in the rate at which CO2 is being removed from the atmosphere in the biosphere, very similar to the notion of what ecologists call net ecosystem production. And I'll define some of those terms as I go forward. Of course, this is not how things are analyzed in life cycle assessment. And so we're going to then say, well, okay, what went wrong with LCA as we've been doing it. Those of you who've been working on any aspect of this issue know that the analyses that have been done are really fraught with uncertainties. Biofuels and their value for a lot of things, including climate, were debated for a lot of years. And then as climate mitigation policy went forward and we put in place nationally the RFS, as California put in place its low carbon fuel standard, as the European Union put in place its renewable energy directive with its liquid fuels components, these debates became even more fraught. People did analyses and said, okay, well, this has a certain reduction in carbon intensity. But there's a lot of debates about that. And of course, when the land use issues were put on the table for the first time in a really quantitative way, linking to these analyses by the science papers, now classic science papers, by Searchinger et al. And Fargione et al. In Science in 2008, the debates have become even more, shall we say, dramatic. A lot of the work that we've done as a society on biofuels and on transportation and climate policy had its start in the 70s with what is the oil crises before a lot of your folks' time, but for me personally, a formative moment. That's when I started working on energy, is in the late 70s. And, the paradigm is that we need to produce a different form of energy than fossil fuels produce petroleum. And so, at this point in time, I sort of say, well, what are we running out of? Oil or atmosphere? We've not run out of oil. It's more specifically, we've not run out of fossil hydrocarbon resources that can, at costs that appear to be affordable, even at $100 a barrel, to the private market, can be easily enough converted into convenient liquid energy carriers such as gasoline, diesel, and jet fuel. So I'm going to focus not on replacing oil, which is the traditional motivator of work in this area, with the assumption that if you replace oil with a renewable fuel, then you get a carbon benefit. That's the traditional assumption. I'm just going to focus on the mitigation problem associated with liquid fuels in particular. I like to make a contrast conceptually between solving a production problem versus solving an environmental protection problem. In energy circles, we often don't distinguish those, and I think my work underscores the importance of being clear about what we're trying to do. Protecting the environment is not reducible to a production problem. And oh, by the way, markets do tend to take care of production problems pretty well. They might make a big mess in the process, but we don't have an energy production problem in the world. We do have a huge problem associated with the way we use energy that sends carbon now into an unmitigated one-way trip into the atmosphere. So that's the problem I'm going to work on. I'm not trying to replace petroleum. And I call that problem the liquid carbon challenge. This will be the title of a paper that's now in press. I'm going to give a little bit of the talk will be content from that. But where I've come after looking at these biofuels for a few years and thinking about this issue, come to think of this as well. It's a liquid carbon challenge. We know transportation's highly reliant on liquid fuels. They're perhaps the ideal energy carriers. If you want a liquid energy carrier that doesn't have a carbon backbone, well, hydrazine comes to mind. That's like ammonia. Ammonia is not really a liquid. It's not hard to compress into a liquid, but the next liquid up is the N2C, or no, N2H, whatever it is. Forget that part of the chemistry, but it blows up really not easily. I don't think we're going to have hydrazine cars. I hope not anyway. And, I think anybody who knows basic chemistry should understand that on a vehicle, carbon capture is just not feasible. So, the normal paradigm has been, well, we can address, the liquid fuels by limiting the demand for energy-intensive modes of travel, reducing CARB EMT, using high-speed rail instead of air. We can improve efficiency, or we can switch to non-liquid energy carriers such as electricity and hydrogen. And, of course, here, ITS and you guys are one of the world centers for work on figuring that out. So, all well and good. Meanwhile, back at the ranch, liquid fuels remain the world's #1 source of commercial energy. And I'm going to show you, kind of the carbon curve, and you see that growth has been pretty steady. Also, liquids are liquid. Well, duh. But what that means is that they're readily tradable. That's what, the fact that, they're really good for putting in cars and moving things around, or jets, also means it's the easiest form of energy to move around. So we have global trade in liquid fuels and feedstocks. And even as we move into the biofuel realm, the reality is those feedstocks are not quite as easy to move as crude oil, but they're globally agriculturally traded commodities as well. That means leakage is not a side effect. Leakage is a front and center issue when we think about this problem. Whoops, this didn't translate well, but I think you get the gist of it. Here's where global transportation energy use stands. Gasoline, diesel, jet, the bar that had an error is residual oil for ships, and then a tiny bit of liquefied petroleum gas. That's internationally. U.S., of course, we use a bit proportionately more gasoline than the global average. I want to show now the carbon trends, and up through about 2011, and these trends more or less have continued. Coal has overtaken oil as the world's #1 source of CO2 emissions, largely through demand growth in Asia. We see oil, in spite of some ups and downs of the world oil price, the trend line there is just sort of a steady growth trend. Natural gas, steady growth, probably picking up, a bit. And then where we've made progress is, of course, in reducing deforestation. Sees measurable progress in this global picture. It turns out in round numbers, on a carbon mass basis, not CO2 mass, but carbon mass, so that's 12/44 of CO2 on a molecular weight basis. These things kind of more or less round out currently to 4.321. So the flow from the human economy of CO2 from our use of liquid fuels, which is almost all derived from oil, fossil liquid fuels, this doesn't count biofuels, is about 3 petagrams of the 10 petagram total anthropogenic CO2 that is roughly the current situation. Now, I also want to point out biofuels don't show up in here. Of course, that's small, and that's correct. When you do a global carbon accounting, biofuels are carbon neutral because whether the biomass is consumed by you or a cow or other organisms that feed on plants and then metabolized into CO2, or whether it's consumed in the form of a fuel and burned for its energy and released CO2, you have this on an roughly annual basis, this recycling effect that goes on that everybody knows about. And so when you do a global accounting correctly, and this is consistent with IPCC inventory conventions. This is from the Global Carbon Project. You don't count biogenic CO2 in the inventory, and then any effect that might happen due to expansion of human use of land for production and the resulting carbon stock releases shows up in the land use change sector, here indicated as deforestation. So when your system boundary is the whole globe, yes, biofuels are carbon neutral. So I just wanted to, there are conditions under which biofuels are carbon neutral, and one is when you count the whole globe and do this kind of accounting. Here's what global biofuel production has been. We see the big ramp up that we all know about that's occurred over the past decade. And now, Brazil, back at the beginning of the 2000s, was the world's largest biofuel producer with their big pro-alcohol program. And then as the United States put in the RFS, we're now the world's largest biofuel producer, and that our intermediate shade of green here is ethanol in the United States. And then we have some biodiesel coming into the mix too. If you convert this from gallons and count how much carbon is each gallon of each different fuel, that works out to about 0.05 petagrams per year. So the point of reference for that, we're putting in through biofuels 0.05 petagrams of carbon compared to, say, 3 petagrams that comes from fossil-based liquid fuels. But of course, that the CO2 there on a global basis was removed from the growth of the feedstocks. We look, down at the United States, and really is true globally. Essentially, all biofuel production comes from nature's fuels, sugars and starches and plant oils, and they also come from productive land that could be used to grow other things. In fact, when we make ethanol, it's number 2 field corn. Feedstock's a fungible commodity. Same field might be supplying ethanol as is supplying traditional food and feed. In fact, we have integrated mills that produce both and things like that. Same with soybeans. Our number 1 source of biodiesel in the United States is soybeans. It's commodity soybeans. Europe uses various other seed oils. So we're using productive land, and that makes sense because if you're commercial enterprises, there's commercial incentive to do this. You want to do it the most economically efficient way, so you want to use productive land. U.S., where things recently stand, of course, as you know, EPA has proposed to put the brakes on the ramp up for the coming year. Controversial proposal, but certainly one that I support. And but where we've gotten is about 12 billion gallons of ethanol, mostly from corn. We are getting some from Brazil. About 1.3 billion gallons of biodiesel. And we had the first non-trivial production of cellulosic fuels in 2013 of about 860,000 gallons, largely from the Kior pyrolysis plant. First cellulosic production that's sort of broken out of truly just plain pilot production. But that's still a pretty small number. Those of you who know RFS policy know that the target for cellulosic biofuel in 2013 set by Congress was 1 billion gallons. So we're 3 orders of magnitude below the congressional target so far. And then there's lots of activity. It gets lots of press, but is well below the statistical noise in terms of production. And if you add that up, that roughly 13 some billion gallons together is about right now 4% of U.S. transportation energy consumption. So here's the traditional paradigm. As I said, when you do global accounting according to IPCC conventions, you don't count biogenic CO2, and it's correct because your land use sector is part of that accounting. With the life cycle, when we do a LCA, our system boundary is defined by the product system and things, the inputs and so on related to the production of the product. So this is the traditional view. Again, here now within the confines of the product system, we have carbon neutrality in that the CO2 emissions from combustion, go into the plant growth. Diagram courtesy of our good friends at the Renewable Fuels Association. So biofuels are also carbon neutral within a life cycle as defined, as traditionally defined. So say, okay, carbon neutral. Sounds good. What I want to do now is a thought experiment to look at a condition under which you don't see the carbon neutrality. And, before I jump into that, I want to take, the next step here. But, the thought experiment is going to involve this biofuel here. And the way we traditionally do things, the way it's done for the low carbon fuel standard, is we compare, this system boundary of the biofuel. And I'll leave this indirect land use change out of the picture now. But the traditional LCA, you draw your system boundary like this. And of course, within that life cycle as defined, we have the carbon neutrality, just like the pretty diagram before, where the biogenic emissions, the tailpipe, the beer bubbles, are neutralized by the uptake during photosynthesis. And we compare that to what appears to be a similar system for the fossil cycle, starting with oil extraction, petroleum refining, and so on, the vehicle emissions. So you do this else life cycle, come up with a number, compare it to that life cycle, and that represents the, what people have traditionally thought was the benefit of biofuels. Now, as you know, what happened is said, well, whoops, there's some displacement effects here. The corn that used to be used for feed and food is now diverted to fuel, and there's this chain effect that results in deforestation. So there you have the indirect land use change. At least through CARB's determinations, and I think most work, this is very significant for the biofuel. There are some indirect impacts for petroleum, but at least in terms of how they're scored, those are very small. But this is big and uncertain. And of course, folks here have been working on that issue. And, your colleague, Rich Plebin, of course, has done a great job of characterizing those uncertainties. And of course, they also have done a good job of criticizing why this framework, this attributional LCA, which is this, just this part of the diagram is the traditional attributional LCA without looking at these consequential effects, why that can be misleading. So I'm not going to repeat that work. I certainly think that's a great piece of work they did, pointing out that liability largely related to a lot of uncertainties and that type of thing. So this is what we normally get. And this is from the CARB lookup tables when you do these LCAs. So, and this is just for sake of illustration. I'm not trying to make points about what the numbers are, because I frankly don't believe any of the biofuel numbers. So, but we have for gasoline, the tailpipe is in blue. The upstream production emissions are in pink. Leaving out the iLUC for now, the traditional comparison is you don't count the tailpipe emissions or any processed biogenic emissions for the biofuel, and so you get this difference here. And then, California looks better. Sugarcane looks better still. Similar pattern with the diesel. And then, of course, people put iLUC in and debate that. But the point is that comparison, LCA comparison using these system boundaries, results in numbers like that. So this brings me to the thought experiment. And the challenge here in doing this is I want you to set aside the life cycle paradigm in your brains, as comfortable as that is. And to paraphrase Bill Clinton, I want you to imagine yourself as the atmosphere and feeling the pain of the atmosphere of CO2. And that you're looking down on the land and human activities, and you're seeing CO2 coming up at you, and then you're also seeing CO2 leaving you, the atmosphere. And you're paying attention to where this is happening. So you're just looking location by location at where the CO2 fluxes are occurring. So upward flows are adding to your pain, adding to the CO2 concentration in the atmosphere. Downward flows are relieving some of that pain there, taking CO2 away from you. And what I want to do for this thought experiment is I want to hold constant the rate of liquid fuel use. We know that if we dial that down, we dial down the demand for gasoline, diesel, and so on by things we know, VMT reduction, vehicle efficiency. That's good. So let's assume we've done as much of that as we can. So that's kind of fixed. And I'm going to also hold constant crop yields. We know there's an intrinsic gain in crop yields, or at least there was up until, I'm going to show you a U.S. corn yield recently, and we see, well, it's always got weather effects in it, but it doesn't look very good in recent years. But, again, we're not turning that dial either. And, globally, it's been very difficult, and in fact, people debate whether human activity on balance has increased net primary productivity or not. We know that when you do, convert land and put it into production with high inputs, you can beat nature's primary productivity in some locations, but in a lot of cases it actually land conversion results in a decline in MPP. But anyway, that's what I mean. We're not going to mess with that. So the land is kind of doing whatever it's been doing in terms of, of taking carbon away and putting it into the form of biomass. And I want to look down as the atmosphere and say, well, what happens when some of the annual uptake on a patch of land, a cornfield, a soybean field, is shifted to produce fuel, displacing fossil carbon? What do I, as the atmosphere, see? Well, again, this just iterates my, excuse for holding yields constant. This is the long-term growth in yields, and then we've got hit in some bumps. This was the big drought. We've not planted a lot more land. It's kind of, it's not quite at its historical high, but, as we gain productivity and so on. But, and then, again, iterating that this shift quantitatively, I'm asking to think about what happens when productive land, the disposition of the biomass shifts from whatever it was being used for to fuel. And that we have seen a huge shift on cornfields across the country as the ethanol share went from whatever it was around 6-7% early part of the decade to it's over 40% share now. So I just want to say we have seen the shift that I'm talking about in this thought experiment. Turning to the emissions side, the car, just to reiterate the fact of chemistry that for most carbon-based fuels, the CO2 per unit of delivered energy varies within a pretty small band. So, yeah, ethanol is about 2% less than gasoline. This is not a life cycle number. This is just the direct combustion emissions. Biodiesel is actually slightly more than diesel. And the common fuels are about 72 plus or minus 2 grams of CO2 per megajoule of lower heating value. So that part of the thought experiment, as we've shifted some land to ethanol and then ethanol substitute for gasoline, the atmosphere is looking down at the tailpipes and not seeing any difference. Same amount of CO2 flying up into the atmosphere. What's going on the land? Well, the amount of CO2 taken up by plant growth does not vary depending on the disposition of the harvest. A cornfield, sugarcane field, whatever, fix a certain amount of carbon, and that gets removed from the field, and something gets done with that carbon. Now, if you have previously fallow land, and or you say remove residues that might otherwise be decaying, then that would increase. The atmosphere looking from one year to the next would see, oh, this patch of land, is removing more CO2 from me this year than it was last year. But for the vast majority of what's gone on with biofuels, both in the United States and globally, the atmosphere is gazing down at this cornfield and it's seeing the same amount of CO2 leaving it. So there's no change in CO2 removal. There's been no change at the tailpipes. First order, the atmosphere is in just as much pain this year as it was last year. First order, there's been no change in the fluxes, feed source of the feedstock, or at the tailpipes. So there's like zero carbon neutrality to first order. Atmosphere hasn't, isn't any better off. Now, yes, there's displacement effects. Because even though the atmosphere sees this patch of land that has been still growing corn, still removing the same CO2, last year that was going into the food and feed chain. This year it's going into the fuel market. We've displaced some stuff in food and feed. And of course, this is all the displacement stuff, ripple effect that we all know about. So if there's been a reduction in CO2, it's of the form that, well, this displacement of corn has raised the price of tortillas. And so the campesinos, people in Mexico or whatever, who have a serious food budget challenge, or maybe eating less tortillas. There's a CO2 reduction benefit from that, but it's a second order effect. We know food and feed demand is by and large inelastic, but that's not the kind of benefit that y'all had in mind when you passed the low carbon fuel standard. You weren't claiming that the benefit from the use of ethanol to displace gasoline was coming from starving campesinos or otherwise creating deprivations in the food market. Claiming somehow that this neutrality that was happening in the life cycle was really what was going on, and you didn't have to count any of the carbon from the tailpipe. But, atmosphere, it's not what the atmosphere sees. And yes, some carbon's been left in the ground, but the atmosphere has not seen a difference in the amount of CO2 on balance coming up into it. So I wanted to walk through that verbal example to try to create some, just physical reality about the math that I'm now going to go through. So this is the paper that I did, and again, as I noted, we've been debating these things for a lot of years. ILUC in particular, the land use question, highlights some methodological issues. So I wanted to go back to basics and go back to the fundamentals of carbon cycle accounting. And ultimately, I would like to seek methods that are data-driven, that rather than reliant on very complex modeling, because these now consequential LCAs, they're not verifiable in any scientific sense of the word. So I want to, basically do something where I can maybe have some hope of invoking the principle of what gets measured gets managed. So I want to start, refresh you all on the global carbon cycle. We have, different flows up and down the ocean, and the one, that's of course most relevant for what we're talking about is this terrestrial flow here. And, on a global basis, we recycle about 120, this is in petagrams per year altogether. And the Earth is still, by and large, on a terrestrial side, a net sink, even in spite of everything we do, including land use change. It's still, the world is still a net sink. And of course, that net carbon accretion, ultimately, some of it goes into long-term soil carbon, some of it gets, eventually makes its way to fossil fuels. Maybe, we have peat forming in wetlands and things like that. And then, we have this fossil flux here. This chart, is in a new book, but it was, I think the data are 2007. So it's, now the 2011 data, this is 10, that was 8 then. It's still climbing. And I want to now home in on the terrestrial part of the equation here. And define some terms. This is a diagram, from like a book on ecosystem productivity. The 120 that was on that other chart, that's gross primary productivity. So all the autotrophs, largely plants, but also any other kinds of autotrophs, which are organisms that essentially make their own energy using sunshine and moisture and the raw material of the world, fix a certain amount of carbon, and that's gross primary productivity. Now, they have to respire some of that themselves just to grow and operate their own selves. That's autotrophic respiration. And that is about half. So about half of gross primary productivity goes back up into the air, as plants respire and so on. What we look at is net primary productivity. That's the basis of yields, the basis of the food chain. Everything other than plants that eats plants to live uses some of that NPP. And the part that we and largely decomposers, or as most of this heterotrophic respiration goes back up into the air. Then what's left is known as net ecosystem production, the amount of carbon, and that's the small, relatively small number. So if you remember, like the 120, about half of that is MPP is about 60, and then NEP is about 3 from that other chart. And then we have these disturbances, land use change events, natural fires, or the deforestation that we cause. And so we have these large episodic losses of carbon, and that's the land use change flux. And that, one recent estimate of that is about 1.5 petagrams. So my model is going to work with the terms I circled here, and I'm going to abbreviate NPP as just P, heterotrophic respiration as R, net ecosystem production as N, and land use change as L. Just, incidentally, some of you may know that, this is often called net ecosystem exchange by the people who do eddy flux measurements. People go out and put towers over forest and try to actually measure that directly, for example. So here's the model. We've got a complete model of the interaction of the terrestrial biosphere, the geosphere, and the atmosphere. I've left out the oceans, but same thing if you wanted to throw oceans in. But we have a liquid fuel energy system, and I'm just looking at the core carbon cycle here. I'm not looking at conversion, energy conversion. So I'm not looking at the losses of when you distill ethanol or, all that process energy, because that's all, we know that's, more emissions. I'm just trying to get at the core carbon balance here. And essentially what our liquid fuel energy system does is it takes fixed carbon from some source, either fossil reservoir or the biosphere, burns it, provides us motive energy, and releases CO2. So the carbon flow is, the fossil carbon flow I've designated by F, the biofuel carbon flow I've designated by B, the emissions carbon flow is E. Well, we don't have any practical way of going directly from here to there at meaningful scale. Well, yeah, there's some mineralization, but that's like really slow. People are working about direct air capture through chemicals. Well, that's pretty exotic. So there's no way to go from here directly to there quickly. Things do go from here to there over eons. So what we have to work with is net primary productivity is the CO2 removal mechanism at hand. Most of that goes back out through respiration. And then if we mess with the terrestrial carbon stock, we get these land use changes. Point is, and I have solid arrows are flows interacting with the atmosphere. Using biofuel or fossil fuel itself to the car doesn't interact with the atmosphere. So right here you see that it's just substituting carbon from here for carbon from there doesn't change the emissions. Because again, we're just, we've done what we can to improve efficiency and all that. So I'm looking at constant emissions from liquid fuel use. And, well, I could have used my animation. I just defined all these terms. There's the cute animation for it. So this is really a first-order model, stock and flow model. I just really explained what I wrote on this slide. Key thing here is that this is an inherently dynamic model. I'm looking at a step change. I'm not looking at an equilibrium system, but I'm looking at what happens when we shift our source of carbon from fossil to bio. And so it's a dynamic comparison, rather than equilibrium systems. And I'm also looking at carbon fluxes in situ, meaning just like the thought experiment. I'm looking at where it's happening, not blurring it over and trying to average over a life cycle. And I want to use this model to derive the conditions under which an increase in biofuel use benefits the atmosphere by reducing the net CO2 flux into the atmosphere. So if I take these terms here, let's say, okay, well, whatever we do, we don't want to exacerbate land use change. That's bad. We don't want to do something that throws up a lot of carbon all at once. So I'm going to hold L0, delta L0. What the atmosphere sees is the difference between E and M. Because I'm not changing E, to reduce flow into the atmosphere, you have to subtract N, which is this difference between P and R. So how can we do that? Well, we can increase P. We can increase net primary productivity. If we do that and devote that gain in P, so delta P is positive, so P1 is greater than P0, we get a B1, an increase in B. We have increased the net flow of carbon from the atmosphere into the biosphere. And it therefore offsets the E without affecting the terrestrial pool. And the benefit, the flow to the atmosphere now decreases by B, B1, which is the difference in primary productivity, that, the gain in primary productivity that we somehow have accomplished. Therefore, the mitigation benefit comes from effectively enhancing NEP by improving P, somehow. Case 2, reduce respiration. Basically the same logic. So we're going to keep some respiration that was otherwise happening from happening and use the carbon that we've now kept fixed to substitute for fossil carbon. Difference in R is this B1, and that's the reduction in the flow into the atmosphere. And again, it translates to an effective increase in NEP, this time by reducing what's coming back up at the atmosphere. And of course, this one I think is the one you can most easily understand in a way. It's what use of, quote, wastes would do. So if you have corn stover that 1 year is just decaying and releasing its carbon, and then you take that patch of land, remove that stover. So now, again, the atmosphere is looking down at the patch of land and seeing less carbon coming back up at it, and then substitute that for the fossil carbon, you've got a mitigation benefit. Bottom line is that an effective gain in net ecosystem production is necessary to have a climate benefit. If the biomass was already being removed for other purposes, there's no change. Yeah, it's just like the thought experiment I did. There may be displacement effects, but those are secondary. It doesn't matter whether the biofuel is first or second generation. Where second generation comes in is it provides technology for maybe utilizing stuff that would otherwise decay, or like algae. Another case where if you have a patch of desert whose primary productivity is essentially zero, and then you hang plastic tubes full of green algae liquids, which you guys probably have seen or studied even, and the atmosphere then looks at that patch of desert and it's now removing CO2. So that's an example of a way to do it by increasing P. You found a patch of land where primary productivity was zero. You've started growing something on that land through technology that wouldn't otherwise grow, and the atmosphere is better off because it's removed more CO2. You could take a parking lot in an agricultural productive area, break it up, plant a cornfield. That parking lot is now removing CO2 that wasn't before. So, and that there again through an increase in primary productivity. But the point is that you always have to pay attention to what the initial condition was, the initial state of carbon dioxide removal. And my shorthand way of saying that is you can't rob Peter to pay Paul with free carbon. There's no such thing as free carbon. The biosphere tends not to waste carbon. What we call waste is feeding decomposers. Decomposers happen to be very important. If there's any of you who are ecologists, appreciate that. And that's why, so I know some of you guys are looking at the Stover thing and say, well, how much can we actually remove without disturbing some other things that are going on, the buildup of soil carbon? Another example that I like to use is, what about wastes? Because people say, well, wastes are automatically good. Well, suppose you have a drum of waste oil that you could convert into biofuel. Well, what would otherwise happen to that drum of waste oil? Suppose the alternate disposition of that drum of waste oil was landfill. Stuck it down into a landfill in a steel drum where it stays for decades. If you take that waste oil that would otherwise have been landfilled and substitute it for diesel fuel, the atmosphere is no better off. Because the prior disposition of that oil was a landfill. It was keeping the carbon out of the air. So that's what I mean, is that you always need to look at the baseline disposition of the carbon if it's a productive system as opposed to, say, a waste oil or whatever, that falls into the category of what we call NEP and in ecological sense. But the bottom line is that for a net CO2 reduction to occur from the use of biofuels, there must be an increase in the rate at which CO2 is being removed from the atmosphere. Just put that into, simple first derivatives. For an increase in biofuel use, in other words, B prime to be positive, to have an atmospheric benefit, to make the flow to atmosphere negative with no change in land use. Given that we're holding E constant, you must have the first derivative of what I call effective net ecosystem production to be positive. So let's look at what's going on with the RFS. Well, it's got this definition of renewable biomass. So politicians in their wisdom, advised by many of my good colleagues in the NGO world, came up with this definition of renewable biomass. And there's lots of components to it. I want to highlight this component because that's mostly where we're getting our qualifying renewable biomass, and it's planted crops and crop residues from agricultural land clear prior to enactment and actively managed or fallow on that date. There's been some conversion of fallow land, but mostly we're diverting from already productive land. So we qualify as a renewable fuel. Renewable feedstock, corn, soybeans, qualify. Well, if we go back to what I just derived, we need this effective gain in NEP, higher net CO2 uptake on the land, somehow, an increase in P or reduction in R. How does production on existing land accomplish that? It does not. No benefit. We haven't even started counting process emissions or indirect land use change. And what this means is that even though carbon neutrality is true when you treat the world as a whole and count stock changes in the land use sector, deforestation, and even though it's true within the confines of a circumscribed life cycle, it's not true when you look at real sectors and carbon flows through and from the land. It's certainly not true in the transportation sector, which doesn't remove any CO2 at all. So, even though we like to use LCA to claim that substituting biofuels reduces emissions in the transport, it does not. There's no reduction. That's chemistry. And is there an offset somewhere? Is there more CO2 removal somewhere? Not for any of the, maybe for that 860,000 gallons of cellulosic ethanol from Kior. But again, I don't know what their baseline is, and I do know that they're not doing the right baseline calculation because I'm not aware that anyone is in terms of the change in NEP from wherever they got their forest thinnings. It's plausible. It's probably not the 100% that they're claiming for those thinnings, though. So merely substituting biogenic carbon for fossil carbon is not a sufficient condition for reducing the net flux to the atmosphere. It's probably my most important takeaway point. Yet, for as long as I've been working on these issues, and I dated myself, already from the 70s, everyone has assumed that that was the starting point and that all we had to do was make sure we didn't create excess processing emissions, by the production process. And then people realized, okay, and if we didn't do land use change as a ripple effect. This is a big error. I'm sorry. We have to demonstrate somewhere a net increase in CO2 removal. In other words, fix more carbon than is otherwise being fixed. Not impossible, but that's not what our policies are asking us to do. I want to now move into what went wrong. Well, little known fact, and I guess I can feel good about not having my fingerprints as a policy analyst on the LCFS and more recent, things. But the first paper that was ever written that called for the use of life cycle analysis to regulate fuels for fuels policy, I wrote as first author with Lee Lin, a cellulosic process, ethanol developer at Dartmouth. And we called for a full fuel cycle greenhouse gas standards or a full fuel cycle cap on motor fuels. And of course, full fuel cycle standards is LCFS. That work happened at, we presented that work at Silmar in '95. It was based on, going back now, I guess however many years that is. We were part of a White House committee trying to address motor vehicle CO2 emissions and, kind of hit upon this idea, inspired by Mark DeLucchi's work, actually. Mark DeLucchi presented to us, he had done his earliest work on this here at Davis in the late 80s and early 90s, and we found this LCA paradigm, fuel cycle analysis paradigm, very compelling at the time. We were a bunch of engineers. Like Julie said, I have a degree in engineering. I didn't know any ecology. At that time, nobody was doing anything serious on climate, so it was just sort of an academic footnote. But what happened is then fuel cycle analysis really took off. Mark kept developing and elaborating his LEM model. That spun off into another Davis graduate, Michael Schwinn-Lu Wang's GREET model, and of course that has become sort of the quasi-standard, and of course GREET is now been adopted by CARB for use in the LCFS. You have got GH Genius in Canada, you've got European BioGrace and other models using this paradigm. And then of course, throughout the recent years, the idea of carbon footprinting became just part of the lexicon. And we want to know our carbon footprints, understand our carbon footprints, reduce our carbon footprints. And the common tool for measuring carbon footprints is life cycle analysis. So I wasn't close to the actual development of the recent policies like the LCFS of RFS, but they certainly seemed sensible, when they were adopted. And I think they largely seem sensible to almost everybody in the world still. But they were engineering models divorced from ecology 101, literally not grounded in the most simple basics of the carbon cycle. So if we go back to this diagram here, what's wrong with this story? This is now for audience participation. That's right. It's a baseline misspecification. Go make it more clear with this kind of model from, this is from a GREET paper that, creates kind of another pictorial representation of the same thing in the sense of here's your biofuel cycle here, and here's your fossil fuel cycle here. Here it's kind of looking at the energy flows. But these models basically took those energy flows, attached emissions factors to them, to get carbon flows. And that's what's the matter. What the analysis of the low carbon fuel standard is now doing is, in effect, comparing a biofuel life cycle with land in it, of course, to a fossil fuel cycle without land in it, because you don't use land to produce fuel. But it's as if all the feedstocks were, by political fiat, growing in the desert where there was nothing growing before. So the underlying assumption used in fuel cycle analysis as it's moved into the policy world is to create land from nowhere for the sake of offsetting the carbon from the tailpipe. The models aren't anchored in, they're not grounded in a to use a double entendre, they're not anchored in, what primary productivity. So a correct model is that there's only one system, and that you need to draw the boundary around everything so that your complete system always has land in it, and then examine what happens when you operate this system under different conditions. But you're always going to be counting the CO2 removal on this land, even when you're not using the land for a fuel feedstock. So this is, so the models have all the pieces, they're just not put together in the right way. And then, there's iLuke. I'm not even going to get into iLuke. I mean, that only makes matters worse. Well, to add insult to injury, including insulting myself, because I, in the early 90s, fuels life cycle analysis, that's how we should think about this. During this same period, a different group of people who were primarily forest ecologists beginning to worry about forest carbon mitigation were working on this kind of value chain kind of analysis also, kind of a life cycle analysis. And this is too much of an eye chart, but I just wanted to kind of point some things out about it, because this model from this paper by Bernd Schlangendinger, the late Bernd Schlangendinger et al., called Toward a Standard Methodology for Greenhouse Gas Balances of Bioenergy Systems in Comparison with Fossil Energy Systems. So they looked at this very problem, and they realized that the full system consists of a bioenergy chain and a reference fossil fuel chain. So in other words, they drew the system boundary around the whole kit and caboodle. So they have the bioenergy chain there, and they're looking at the stock change. That's what the triangles are. This is the fossil deposits and net carbon loss from the fossil stock. You can with a biostock, you can have both inputs and outputs, and then you have all the processing stuff, all the stuff we do in GREET and everything else. But then the point is that this all went to, and they did a generalized analysis, whether it's just cars or electricity or whatever, but you ended up with a common output here. And so you operated this system under different conditions, and there are conditions under which bioenergy can be beneficial, but as it typically turns out, you get a little bit of benefit as time goes on, not a large benefit from the get-go. And they admit in their paper they were not looking at leakage, so they weren't looking at indirect land use change in their analysis, but at least they set up the correct conceptual framework here. But unfortunately, this body of academic work didn't cross-pollinate with the whole energy analysis world that led to the policies we now have. So this, so if you want to do an LCA for policy, this basically is the correct way to do it. But what happens now, and we realize that we're dealing with these liquids and they're using tradable commodities, when you begin to think about then, in particular, the leakage effect and the fact that you have displacement effects in terms of use of land, you quickly realize that you've moved from comparing fuels, because we say we compare corn ethanol to cellulosic ethanol. Well, the ethanol is the same, so you're really comparing complex systems that, because of the nature of their feedstocks, are coupled to global commodity markets, global land markets. So you're really comparing world versus world, but thinking that you're just comparing fuel versus fuel. And that is where we've been seduced by this notion of the carbon footprint. And we thought, well, we regulate sulfur in fuel, we could regulate the carbon content of fuel. In fact, we write papers saying carbon content when we mean a different world, a whole world. Unlike sulfur, where you can take the fuel in a test tube, take it to a lab, and determine whether it's got 30 ppm or 15 ppm. And we think we're treating the fuel regulation as if we can do that with the carbon through this complex, globally connected system. I think, again, this contrast to production, we fixation on how do we produce something different than petroleum. We lost track of, well, what we really want to do from an environmental perspective is protect the atmosphere. And then we now have very strong interests behind this. I mean, this story, you can't blame the corn growers and the soybean growers, really. I mean, they're just looking for markets for their crops, and of course, the realpolitik of these policies is more about that than environmental protection. The RFS didn't pass the Senate as part of ISO with a vote of, 86-8, because people were concerned about climate. The idea of moving to renewables has been part of, environmental dogma. I mean, I believed in it. I mean, I still see there's roles for renewables, but I'm much more cautious about just saying, well, we need to get to renewables, so let's just push biofuels because they're renewable. Ipso facto, they're carbon neutral, and if we, produce them right and minimize the emissions, we should be okay. There's a lot of interest behind this now, even though what we're doing is trying to discriminate among alternative modeled worlds, which is not verifiable. And in technical terms, what happened is the interaction with the biosphere is a stock and flow, inherently non-equilibrium problem technically, that we were treating as an equilibrium flow problem with these averaged life cycles. So just in a, methodological sense, it was generally, it's just wrong that way. And of course, the big problem with the error is as Andy put it, misspecified baseline. Existing primary productivity left out of the baseline. And ironically, it's not like the life cycle world had some, they had some wariness about it. If you go, professional LCA people know that it doesn't evaluate absolute impacts because it's always a relative thing, involves averaging over space and time. There's a lot of uncertainties. And then in the case of fuels, there's future impacts. So there are no facts about the future. You can't, when we do this ILUC averaging, is it over 30 years or 20 years? Whether you do 30 or 20, right there makes a 50% difference in the magnitude of the factor. That's a pure assumption. You can't ever verify whether 20 or 30 years is the right number scientifically. But the ISO guidance says there's no scientific basis for reducing LCA results to a single overall score or number since weighting requires value choices. Well, we're doing exactly that when we compute carbon intensities. They're full of value choices. But I'm saying it's worse. It's not just perhaps arbitrary value choices that render it unverifiable. It's also plain wrong in terms of the underlying carbon cycle science. And then even Michael Wang in his encyclopedia article on fuel cycle analysis said they should be used to identify potential system improvements, not to simply show which systems are better than others. Of course, what are we doing with the RFS and so on? We're trying to show system X is better than system Y. I mean, LCA can be a very powerful tool, but the real way it was originally developed in the non-energy realm was to analyze a system and then say, oh, well, here's where we need to, if we improve the system here, if we reduce this impact here somewhere in the supply chain, that's what we should do. So that's the value of the tool. The power of system thinking is to identify the parts of the system where there's opportunities for improvement. But we've slipped into, because of the seductive appeal of carbon footprinting, this idea of trying to use this tool, again, in a way that's just inappropriate from even the sort of professionals of it, who behind it. So to kind of wrap up where things go next, and this is not in my biofuels balance paper, but I'm sort of take those to the next step, some of which is in my new forthcoming paper. You'll know about the three-legged stool. When I teach this, I reduce it to a mnemonic: C equals DEF. The carbon emissions from automobiles or some other transportation sector are essentially a product of travel demand, VMT, the vehicle energy intensity, inverse fuel economy, and then we've been saying fuel carbon intensity, thinking in the life cycle, but I'm going to say, well, that's the greenhouse gas impact of the fuel system. Realize we're dealing with a system. So let's think about what that means now, as implied by the kind of analysis that I just did. Well, if we want to think about the mitigation options, with this three-legged stool, we can limit VMT, we can improve vehicle fuel economy, reduce the greenhouse gas impact of the fuel system. So now, how can we do that? Let's parse that as opposed to treating that as a LCA construct, because we know, well, that breaks down, especially breaks down for biofuels. Well, one way is to use chemically carbon-free fuels like electricity or hydrogen. So that's great. No more CO2 from the tailpipe, and what we have to do is then control emissions somewhere else. And of course, that's part of the appeal, that somehow central electricity or hydrogen generation will be able to control the emissions more easily than we can control tailpipes. So, but the point is we're out, the mitigation option now, we've stepped outside of the sector. So even though we think of the transportation sector as a three-legged stool, here we've essentially thrown the problem over the wall and say, okay, you guys generating electricity, you're a problem. We've got these super efficient electric cars that have zero emissions at the tailpipe. You deal with the CO2. Fine, that's a legitimate thing. Well, other thing, capture the carbon on the vehicle. Well, okay, we can't do that. The other option, because if you're still carrying carbon to the vehicle in the form of a fuel, there's nothing you can do about it once you put it into the tank. So the only thing you can do is balance those emissions with CO2 removal somewhere else. So that again, hello, that means you need to look somewhere else. And as I just showed, you need to increase the rate of CO2 removal somewhere else. The fact that you're already removing CO2 somewhere else doesn't do you any good. To claim somehow that corn ethanol, is carbon neutral, without worrying other than process emissions in your car is tantamount to claiming that eating a corn-fed hamburger reduces CO2 emissions. No, I'm sorry, it does not. You've got to increase somewhere else CO2 removal or avoid releases that would occur. So this is where you get into things like reductions of emissions from forest degradation and deforestation. Or, actually scary, but if you put more CO2 in the ground, through CO2 EOR, of course, it doesn't count if you're mining the CO2, which is mostly what's going on now. But if you're somehow getting CO2 that would otherwise be emitted and sequestering it, well, okay, there's an additional, reduction there. But typically in that case, though, if you're taking CO2, I think ADM is demonstrating, from an ethanol plant, CO2 enhanced oil recovery somewhere in the Midwest. There's not an additional removal there. You're just avoiding the emissions that would have occurred at that ethanol plant. So that kind of CO2 EOR, well, there's an emissions reduction benefit. It's not really a transportation sector benefit. It's an industrial sector benefit. So the way to look at this now, and this is a chart from my forthcoming Liquid Carbon Challenge paper, is a binary logic tree. So instead of the three-legged stool, and this has some parts of it in it, the logic that I just went through can also be broken down like this. You have fuel-related CO2 emissions. It depends on the level of fuel consumption. And then that has the two legs of D and E legs, the travel demand and vehicle efficiency leg, or it's air travel demand and aircraft efficiency, whatever you like. Then the fuel impact of the fuel. That cleanly parses into, does the fuel have carbon in it or not? Non-carbon-based fuels, well, there's electricity or hydrogen. If you want a liquid that's not got carbon, well, you do have some choices, but they're not very practical. If you carry carbon to the vehicle or the airplane or truck or whatever, this is a dead end. So you have a CO2. Again, it's just another way of representing that the liquid carbon mitigation problem is a CO2 removal problem, a challenge of removing more CO2 somewhere in the world that is otherwise being removed. And the mechanism we most have available is still photosynthesis is the only CO2 removal mechanism mankind has at its disposal at meaningful scale. So liquid fuels are going to be around in spite of our best efforts. So we still have to work on them, this part of the mitigation problem, while we try to work on ways of minimizing their use. We need correct carbon cycle accounting in light of the coupling of these systems. Key takeaway, replacing biogenic carbon with fossil carbon is not a sufficient condition for reducing the net flux to the atmosphere. The necessary step is to increase net CO2 removal upstream. Terrestrial carbon management, that's managing carbon on land to increase the terrestrial sink or things like that. There's no benefit from downstream fuel substitution. Again, that's chemistry. So we, like any other good academic talk, more research is needed, but this kind of upsets the apple cart in this area a little bit, so to speak. So we do need to reevaluate our carbon accounting methods, validate them against real-world systems at market significant scale. You can't, the errors may be smaller for, say, waste-based or cellulosic fuels, but as I would put it, you can't justify flawed modeling by invoking fantasy fuels. What's going on is, and it's the commercial imperative, if we're in a expansive world policy saying get biofuels, producers are going to go find those biofuels the most economically productive way they can, and that's using land that competes with other productive use of land. So you can speculate about marginal land, but marginal land is marginal because it's not very productive. Commercial producers aren't going to do that naturally. And then we also, to me, this is also clarifying the near versus long-term mitigation. We might be able to imagine, as people do with, say, integrated assessment models, imagining that we've got cellulosic conversion technologies and we've got land use managed just so they show a lot of biofuel-based mitigation. But those are, well, just so stories in a sense. What can we do today to move, in that direction? Where are the opportunities for mitigation? We have to look for ecologically sound and economically feasible CO2 removal options as the first step. And, this has implications for where we put our R&D. There's implications for how we teach this stuff. And it has implications for public policy. So really, as far as I've gotten on this, is to really put these issues on the table. So thanks a lot, and look forward to your questions and comments.
We're almost out of time, but
Well, I went on a lot longer than I thought, but
whoever wants to stick around.
I don't have a time constraint at my end, but yeah.
Wants to stick around now.
Yeah. Hey, Andy. Yeah. Mm-hmm. Yeah, yeah. I mean, it's the potential mitigation there, but the baseline always matters. Is again what I'm saying. Yeah. Mm-hmm. What could work? Yeah.
And secondly, even fossil fuels,
Yeah, I mean, you got to do a lot of offsetting somehow. Yeah.
I keep thinking, you're sitting on this huge mass of fuel stock when you're making ethanol, for instance. And most of the carbon that's used for ethanol is the waste product, so to speak, from the ethanol production. Can you sequester the carbon in that waste product?
Well, there's actually not a lot of waste from corn. When you harvest the corn kernels, the residue is, the stover is called, the stalks and leaves. But corn, our modern corn, we are corn men, as people have written. If you've ever been in a modern corn mill, the utilization of that kernel is very high. There's very little, quote, waste. We're right now in corn, whether it's going into feed or fuel. Yeah, well, if you ferment, then that's right. There would be the waste CO2, and yes, you could capture that. That's, in fact, ADM is a demonstration plant doing just that. But that, again, that's, again, industrial emissions control. That's not helping mitigate transportation. It is a way of getting carbon out of the atmosphere that would otherwise go in, yes. Mm-hmm.
Okay, I guess it's not entirely clear to me how isn't not releasing a fossil fuel the same as sequestering it?
Yes, it is. If you don't use the fossil fuel, you are keeping that carbon in the ground.
Are you arguing that? I mean, you didn't say it, but I wonder if it lies on an underlying assumption that we're not actually displacing fuel.
Well, we are displacing fossil carbon. Go back to the basic box model here. In other words, if if you leave this in the ground, fine. One way to do that is to reduce E. Okay, but shifting from here, where are you going to get that carbon then? Now you could mine the biosphere, and we in fact. It's kind of, with indirect land use change, that's kind of what we're doing. We're mining the biosphere in a very messy way. But in that case, we're leaving fossil carbon in the ground, but we're then removing biosphere carbon that otherwise would be fixed. So, this is what I mean by just substituting B for F. There's no change up there. Itself does not suffice to reduce the net flux of the atmosphere. You have to get this biomass carbon. If you don't want this to be disturbed, you've got to play with one of those things. So it's
So even if B is smaller than F.
Well, yeah. I mean, I'm really working with delta B's and delta F's here. So if I make delta B positive and use that to make delta F negative, I've got to get that delta B from one of those two places. If I don't, if I'm just rearranging the carbon in the biosphere and displacing something that was otherwise being used differently in a way that I've not changed these than the fact that I've left carbon in the ground. The atmosphere doesn't know the difference. Well, it is, yeah. That's not a good thing. Well, that's right. Yeah, that's right. That's right. You know, I'm not talking about. I didn't. That's what I mean. I didn't try to reanalyze iLuke. You know, I didn't get into the leakage problem. So, in other words, I'm just looking. That's right. Yeah, it makes it even harder. Yeah. Mm-hmm. Yeah. The hardest thing that I find that people have to deal with is like what was your name again?
Auntie.
The question that somehow by the fact that we're leaving fossil carbon in the ground, that's not automatically beneficial. I'd say that's the kind of the biggest hurdle. That people it just seems so counterintuitive or counter to the way people think, and I think the key there is to recognize that this is you need to show not what stays fixed in one place or another. You need to show where the CO2 is removed from the air. So it's not an emissions problem. What I've done, this analysis, is I've converted what we thought was an emissions problem and reduced it to a CO2 removal problem. And the key reason is that as long as we're losing liquid fuels, that E term, that emission doesn't change as a factor of chemistry. So that's the conceptual leap. We're so used to equating fossil, emissions reduction with fossil reduction that for the case of liquids, we don't understand that what's really needed is CO2 removal. So it just takes a while to digest that, I think. Well, no. It doesn't matter where you remove it to mitigate. Right. Yeah. And the claim that the claim that biofuels mitigate transportation, in a true scientific sense, they only do because of feedstock uptake, which is not happening in the transportation sector. And we've just because our life cycle thinking has had us collapse that to the finished fuel product, thinking that, we use the term low carbon fuel. I would like to ban that term from our vocabulary because the fuel itself, the measurable fuel, has the same amount of carbon for all intents and purposes. And it's kind of this misleading construct that, the core fuel itself is carbon neutral. Because, no, it's not. It's got carbon in it. And you're already implicitly invoking an action in another sector because of the feedstock. So another corollary of this, I wrote 2 papers back called Factoring the Climate Challenges, all about what does the three-legged stool really mean. I basically point out that you cannot completely mitigate transportation sector emissions in the transportation sector alone. That just, again, you can deal with D, demand, and E, but dealing with the fuel factor always involves another sector. Electric vehicles, okay, other sector. With biofuels, if they work, it's because there's CO2 removal somewhere else. So it basically means is we can't, and we kind of know this because we've been doing, LCA kind of does this, but it just sort of collapses things for us. But transportation cannot be, quote, decarbonized in isolation from a decarbonized broader upstream world of upstream resources, whether those are biological resources or non-biological, like direct solar.
It's not necessarily back. I think that it's over.
That's right. Yeah, that you can't. The land is always part of the equation. Yeah, I mean that was yeah, I mean yeah.
It's interesting if you look in the pre-industrial era where presumably all of our energy was more or less coming from
It was.
and very little from fossil fuels. And then we gradually transitioned to a world where we were using 80% fossil fuels. And as that happened, the atmospheric concentration, some of that was probably land use, but some of it had to be, I think, the fossil carbon going into the atmosphere.
Oh well, most
So
of it's
if you
fossil
integrate-
recently.
Right. So if
Yeah.
you integrate over a long period of time, the fact that you are taking fossil energy out of the bank, out of the ground, and putting it in the atmosphere does lead to an increase in carbon concentration in the atmosphere.
That's right.
So this view says it doesn't matter what you substitute, but yet if you look at that long-term climate record, it looks like it does matter.
Well, if you look at the long-term climate, anthropogenic CO2. In fact, this is nicely summarized in the new IPCC AR5 summary. They have a table or discussion somewhere in there that points out that, prior, I think from like 1750 to 1900, or pre the big fossil ramp up, most of the anthropogenic carbon was from biomass burning. We deforested vast tracts of North America, and so yes, in the last 100 years or so, we've used fossil fuels, but of the carbon that's up in the atmosphere, cumulatively from anthropogenic sources, a very large chunk is that we mined the biosphere. They have the numbers in there. Yeah, they do. It's in the AR5 summary for policymakers. So it's, yeah, I mean, the atmosphere feels the pain the same way if you burn a bunch of trees.
Right. I agree. I guess one of the messages from this is kind of, well, it doesn't matter whether you leave fossil fuels in the ground or not. And I'm wondering over a long time period maybe whether it does, and you need to look at all.
Well, I think it gets increasingly difficult to keep carbon out of the air if we keep using fossil fuels.
Yeah,
so
exactly.
it just what it means is you have to be careful about false solutions.
And well, the other thing is that in the time frame you're talking about, demand pretty much staying
Talking year to year.
And your, I mean, it's a deeper question to know how the availability of this fuel actually affected demand.
Right.
Behind your question.
That's right.
And it sort of drove the increased emissions. And that sort of suggests a deeper dynamic linkage between the form of the fuel and the nature of the demand that this kind of model isn't going to pick up.
Right.
Again, that's not the question.
Yeah. Okay, sure.
And I'm looking forward to Cycling, just because basically we are doing cycling CO2 emissions for so even though we are still emitting fuels no, but I think not from other parts of the sector.
That's right.
So I couldn't be.
Well, that's good.
Hope the dinner was good.
It was, yes. Paisanos was a good
Yeah.
recommendation.
Yeah.
I
Okay.
went there, yes.
Good. I'll try it.
Yeah. I mean, have you ever been to Naples?
Yeah. Not to Naples, but I've been to other parts
Lots
of
of Italy.
Italy.
Yeah. Well, Naples
Yeah.
is sort of, in many ways, standard for pizza. There's lots of good pizza in Italy. So I would say it's good by American reference. The
Yeah.
crust was good, which I think is important because most places make the crust. And the toppings were more standard American. I just had a.
So it was American Italian, not Italian.
Yeah. Well, it's similar to what you would get, but the quality, they made the crust right, which is to me a big.
Yeah, that's my also biggest issue here. Because
Yeah,
the
I
crust
got
is
a,
not
I got the, well, it was one that had the meats. The margarita might be quite good. I don't know. Depends. That should be good. Very simple one with good cheese.
Yeah. Okay, I'll try it. I'll give it a go.
Yeah. I thought it was good. Okay.
Like Greek talk, really enjoyed it.
Yeah.
Sorry, I got to run off to another
No, that's
meeting now.
okay. Yeah, I like whacked out slides. I think I must have gone. I know what I did is I did that. This is the first time I did the thought experiment part. Normally I run through the formal analysis, but I kind of did that in part because of the CERT meeting yesterday where I was trying to talk to most of them, trying to figure out how to explain this in just a concrete way, so I came up with this metaphor of imaginary atmosphere. So that's probably what
I
did
thought it was a really good talk.
Oh, thanks.
It was really, it was great to put it at that level.
I was hoping to get,
Yeah. Well, I have to put it at that level for pretty much everything. Because people have so many preconceived ways of thinking about this in their head.
That's right. I mean, just say the laws of old kind of.
Oh, well. Yeah.
It's good to go through it.
Yeah.
Well, anyway, great talk.
Thanks, Joan. Great to see you.
Yeah.
I guess I need to get it before I get it. Yeah. Yeah.
You know, I wrestled with it yesterday.
I know. Well, it's great that you invested the time to come.
Well, no,
Yeah.
Okay, thanks, John.
Okay, we'll see you around, Jamie. Well, the people who, the Schlamendinger work, those people got it right because they were dealing with forests. So they were inherently, they knew growth and that thing. So annual people thought, I'll give this annual recycling. That's it. But the people who study forest carbon really have to root what they do in the so there's a whole set of work there about, well, you can let a forest grow, and then at a certain point,
Some of the residue stuff makes me nervous. I feel like there's a lot that's so unknown about soil biogeochemical.
well, that's right. Yeah. Well, people are
Because I,
putting
I'll
more-
stover research now. Not just the fixed carbon from the stover.
Well, a good volume was published the year before I don't refer to it in this paper, I don't think, but this is the new paper that
Oh, okay. Great.
but this was a review paper. that really, Lal, Ratan Lal is like one of the world
Yeah, and I mean, I agree. You know, one of the reasons I got into doing life cycle assessment is because I realized that just substituting a renewable fuel for a fossil fuel wasn't enough.
Yeah.
And, you know, we do try to focus on process improvements, but they're not as sexy. I mean, I cringe a little bit every time I'm like, 78% less than gasoline. You know, I'm like, that's not really the point. And if we didn't call combustion emissions biogenic, then it wouldn't be less.
That's right.
But I still, every time I think about it, I mean, it does seem fair to me. Maybe I'm just too indoctrinated by that way of thinking, but comparing to a fossil fuel baseline makes sense to me.
Right. I'm not saying you don't compare to a fossil fuel baseline.
We'll see.
Again, there's no such thing as free carbon.
Sure.
That's the basic way.
But I like to think, you know, as
Yeah.
unlikely as it may be, I like to think that, you know, we may be, you know, affecting. I mean, if you can hold the land use constant, which I realize is unreasonable, I'm already asking too much, and hold demand, you know, okay, fine, at least.
Well, we're
grow
managing
renewables
demand,
along
at least
with
in North
demand.
America
Right,
now.
exactly.
In California, we're actually reducing.
Exactly. Then you end up driving up the prices of, you know, feed for cattle,
That's right.
make people eat less meat. Okay,
Well,
we
that's what I
save
mean.
carbon, you know, so there are
Well,
all
that's
these,
what I mean.
it's like how economics, you know, can't be really considered a pure science. All of these things happen and have effects and, you know, behavior.
Well, it means we should be clear about what we're trying to accomplish. It then affects people who are well, forcing them to eat less. We're not changing what we eat. Prices are,
That's the problem
Food
with every
insecure.
environmental policy. Fix the rate distributional effects.
that's a big question. You know, I mean, it all comes down to